All right, hello everyone. So this first video is going to be uh, the first video in the multivariable calculus series. So I'm going to start off with three-dimensional space, uh, and we are going to learn how calculus essentially in Calc 1 and Calc 2 transitions into three dimensions. So that's what multivariable calculus is about. All right, so first let's think about a point on a number line. So a point on a number line only requires just one input variable. So essentially this is just one dimensional space. So a number line is defined as all the row numbers in one dimension. And we can use any variable, in this case, using x. In two dimensions, we require two input variables, x and y. And you call this an ordered pair usually. So this is two-dimensional space. This is denoted with R2. And this is just a representation of two-dimensional space. We're already familiar with that. We have an x-axis and we have a y-axis. And then we have a point here. But a point in three-dimensional space requires three input variables. And we're going to need three coordinate axes to define the position of that point. So we're going to have x-axis, a y-axis, and also a z-axis here. And usually this is how the coordinate axes are set up. We have an x-axis coming out of the board, the y-axis going to the right, and the z-axis going up. So sometimes you might actually see the x-axis, the y-axis, and the z-axis like labeled differently. You might have this as the y-axis sometimes. This is the x-axis, or I don't know, this is the z. But in the Stewart calculus textbook that I'm using, this is how they denote the axes. So let's do an example, plotting a point. For example, point 1, 2, 3 in three dimensions. So how do we do that? Well, it's pretty much exactly the same as doing it in two dimensions. So we're just going to go one point in the x direction. So this is the x coordinate, this is the y coordinate, and this is the z. So we're going to go one point in the x direction, 2 points in the y direction, and then 3 points in the z direction. So let's try to imagine what that looks like. And the way I do that is by making these little dotted lines. And these dotted lines are going to form a rectangle in three-dimensional space, or a rectangular prism in three dimensions. So this is just to illustrate how the point is positioned in three dimensions. And you want to make sure you're going, the correct amount of steps in each direction. So this is our point 1, 2, 3 in three dimensions. This little point here. So let's talk a little bit more about three-dimensional space. So in 2D, in the XY plane, we have four quadrants. So we're already familiar with that. We know the first quadrant is when X and Y are both positive. The second quadrant is when X is negative, Y is positive. Third quadrant when they're both negative. And this is the fourth quadrant here. So in 3D, we have 8 octants. And you can think about them as having 8 rooms in a building. So the first octant would be this corner of the building right here, the first room in the building where X, Y, and Z are all positive. And then different books always define the other octants differently, so I'm not going to specify which one is which in this case. But let's talk a little bit more about this coordinate system. So we have this plane here, as the YZ plane. And the YZ plane just represents the set of all possible Y and Z values when we set X equal to 0. So it's like a two-dimensional plane in the three-dimensional space. And another plane of importance is the XZ plane. And this is the set of all possible X and Z values where we set Y equal to 0. And then finally, we have our familiar XY plane, which is the set of all XY values when we set Z equal to 0. So these three different planes are like the basis of three-dimensional space. All right, so let's talk about how to plot in 3 dimensions. Well, in 2 dimensions, an equation with X and Y is going to be a curve in the XY plane. So for example, Y equals X squared is just going to be like a two-dimensional parabola in the XY plane. But in 3D, an equation with X, Y, and Z is going to be a surface in 3D space. So any equation that involves X, Y, and Z, or might be missing one of these three variables, that equation is going to be a surface in 3D space. Let's try to plot Y equals 4 in 3D. Well, let's think about it, what it looks like in 2D. And usually that's one of the first steps you want to do when you're trying to plot something in 3D. You want to think about what it looks like in 2D. And then that'll help you visualize what it's going to look like in 3D. So Y equals 4 in 2D is just going to be this horizontal line. And X is not involved in this equation, right? So X is a free variable. So X can be any number. This line goes from negative X equal to negative infinity all the way until X equal to positive infinity. And in 3D, let's think about what Y equals 4 looks like in 3D. In 3D, we're going to have that same line in the XY plane. So we're going to have that same line, but we also have an extra dimension. We have the Z dimension. So now Z is missing from that equation. Z is missing from this Y equals 4 equation. So in this case, we're going to have that X and Z are actually free variables, X and Z. So what does that look like? Well, in 3D, we have we have 2 degrees of freedom. So this is going to look like a plane in 3 dimensions. So something like this in 3 dimensions. And that will extend for all X and Z values where Y is equal to 4. So it's like another plane. It's like the XZ plane, but shifted 4 units to the right in the Y direction. All right, so let's do one more example. So let's plot X plus Y equal to 2 in 3D. Once again, let's think about what this looks like in 2D, just so we can visualize what it's going to look like in 3D. So in 2D, we have the XY plane. Well, let's solve for Y in this equation. So if you solve for Y, you get Y equals 2 minus X. So this has a y-intercept of 2 and a slope of -1. So we're going to have a line that looks something like this, something like that. So this is Y equals 2 minus X. And if we go to 3D, let's try to plot that in 3D. It's going to look the same on the XY plane. We're going to have that. So we're going to have this line here. But once again, in this equation, Y equals 2 minus X. Z is a free variable. So Z is a free variable because it does not appear inside the equation. So in that case, we're going to have a plane. Once again, we're going to have a plane that looks something like this. This is our plane, x plus y equal to 2. All right, so the next topic I want to talk about in 3D is the distance formula in 3D. So we know that we can find the distance between 2 points in 2D by just using the Pythagorean theorem, right? If we just draw a right triangle between the 2 points, we can find the distance. But in 3D, you can do the same thing. You can actually use the Pythagorean theorem. You have to use it twice, and you can show that the distance between 2 points, let's say we have a point P2 with x2, y2, and z2 coordinates, and we have a point P1 right here with coordinates x1, y1, and z1. We can find the distance between those 2 points by using this formula here. So essentially, this is just like an extended version of the distance formula in 2 dimensions. Now we're just adding this z component. So let's illustrate this with an example. Let's try to find the distance between point P1, which has coordinates -2, +2, -2, and point P2 with x coordinate 3, y coordinate -2, z coordinate +4. Use the formula to find the distance. All we have to do is actually just plug in the numbers into the formula. But we have to decide which one is going to be x2, which one is going to be y2, z2. Let's make it simple. Since this is P1, let's say this is x1, this is y1, this is z1. Since this is P2, let's say this is x2, y2, and z2. Now we plug it into the equation. So we have 3 minus -2 squared plus y2, which is -2, minus y1, which is +2, that's squared, plus z2, which is 4, minus -2, which is z1, squared. And if we do this algebra, we get the square root. This is going to be 5 squared, which is 25. This is going to be, so 25 plus -4 squared is 16. And 6 squared is 36. So if you add all of this together, you get square root of 77. So the square root of 77 is the distance. All right, finally, I'm just going to talk a little bit about spheres. So an equation of a sphere in 3D with center HKL, these are the X, Y, and Z coordinates of the center of the sphere, with the radius of R is given by this equation. So x minus h squared plus y minus k squared plus z minus l squared is equal to r squared. And this looks pretty similar to the equation of a circle in 2D with the center hk. Now we're just adding that extra z component. So this makes it a sphere. And if our sphere is centered at the origin, and that means that h is equal to 0, k is equal to 0, and l is equal to 0. So this simplifies the equation down to just x squared plus y squared plus c squared is equal to r squared. And this is just an illustration of a sphere in 3 dimensions. This is a little drawing I made. Not the best, but it gets the point across. So that's the end of the video. Hopefully this is not too long, but if you benefited from it, please leave a like and thank you for listening.